And my advisor is Dr. Polo and Dr. Hongzhen Li. And I'm happy to share with you my research, which is published in ISM CCS 2022. And my title is LoneNeuron, highly effective visual domain neural children using invisible and polymorphic watermarks. So let me get started. And my presentation will consist of 4 parts: the introduction part, the LoneNeuron, which is our main attack design, the evaluation part, and the conclusion. So let me get started with some stuff about the AI and machine learning model supply chain. And a more of us are using the deep learning today. And however, it's still expensive to train some deep learning models, especially the large ones. It requires a lot of the computer resources and also the data resources. However, fortunately, we can always find the solutions on the online model sharing platforms like GitHub and ModelZoom. We can directly download the pre-trained ones from the internet and do some fine tuning to use them for our downstream tests. Thank you. But wait a moment. Before that, I'd like to ask you questions. So, are we downloading something from somewhere else in the world that we have never met before? So we all know the risk of downloading software from the untrusted sources, and they might contain malwares, and this has been studied for decades, and we have developed the defenses for them. But how about the untrusted AI and machine learning models? So to further investigate into this, we conduct a survey of how users deal with the third parties downloaded from the internet, and we ask them how they examine the security of their downloaded models, and we collect 400 feedbacks from them. So basically, we ask them, have you downloaded the models from the internet before? And what measures have you taken, including the basic validation, fine-tuning, pruning, defenses, and examination of the code. And according to our findings, almost all the participants have downloaded the models from the internet. This occupies almost more than 90% of all the participants from the 4 groups. However, many of them just use the models even without any basic validations. So this occupies 20% for the researchers of machine learning and engineers, and 30 to 40% of the students as security researchers. And what's worse, we found that a lot of them were not examining the source code of the downloaded models. And this is worse for the practitioners like the engineers and students, which occupies about 20% of the students and the engineers, and nearly half for the AI researchers and even security researchers. But we know that deep learning models are not secure at all. They are vulnerable to a series of attacks. And a very popular family of attacks recently is the neural Trojans, which are the malfunctions embedded inside the models to trigger the model to misbehaviors. And actually, when we look at the AI and machine learning model supply chain, any malicious and compromised stakeholder or man in the middle may inject neural Trojan inside the model because they may have full control over the models. And however, we find that we can not rely on the online model sharing platforms to reduce this risk, because we found that none of the existing code scanners can detect neural Trojans because they are functional. And according to our previous study, we have already shown the end users, they just select the security alertness of security of their models. So based on this, we look at a very powerful new tech growth of the neural Trojans we have been proposed recently, which is very powerful. It's the structural code modification test. So to perform a successful attack, we want many design properties. The basic one is the sensitivity, which means that it has high attack success rate. And additionally, we want many fancy properties to make the attackers stealthy. And this includes that the Trojan will only respond to to the input with triggers, but not the benign input, which is the specificity, and the sample specific and polymorphic triggers, which means that triggers will vary from input to input. And the stillness, which means that the triggers cannot be identified by human eyes, and also certainly attacks should be robust against detection and defenses. So here comes to our main attack design. Here shows the attack pipeline of our works. And we call our works LoneNeuron because it's a single neuron that added inside the host model. So after we embed stealthy triggers on the images, and after convolution, they are transformed into features. And after select certain features out of the feature domain, and they are fed into the neuron we have embedded beforehand inside the model. And after activations, the LoneNeuron will generate outputs which will commute the subsequent layer and propagate to the model decision. So how should we generate the triggers to trigger the LoneNeuron? So to do this, we do this by a forward and backward the two-way process. And to start with, we select certain areas in the pixel domain to carry our watermarks. And after convolution, we know that we will select certain features. And specifically, we will select certain bits, after the summer point and combine them into a pattern string. And when it matches the predefined pattern string for the LoneNeuron, it will be activated. So how should we know how should the watermarks in the pixel domain look like? So we actually do this from this construction from the visual domain back to the pixel domain through a process called the convolution, which is basically an undetermined system of equations, and which at almost all cases will have many solutions which correspond to our polymorphic watermarks. So here is a practical implementation of how our LoneNeuron works. So to do this, we need to inject a few lines of code into the code base of the victim CNS. And what's mentioned is that we can further obfuscate the code, as shown in the 4th, 5th, and 6th line, by adding a coding layer to add a magic number to make the code more neat and readable. So how should we change the injecting the neuron? Actually, we do this by freezing the host model. So this will reduce the overhead for training. And the training objective consists of two parts. The first one is the classification part, which is just to flip the output label of the model. And the second one is the regularization of the LoneNeuron outputs, which is to limit the scale of the LoneNeuron output. So it will reduce the effect of injection of the LoneNeuron on the model size. And the training can be done in two ways, either in white box or gray box scenarios. For white box, we need a few shots from the original data set. Actually, we need very few samples. For example, 50 for the ImageNet, which contains millions of images. And all gray box just using random Gaussian noise. And the outputs can be significantly improved to further reduce the amount of parameters we added. So for the evaluation part, we selected the 4 data sets and MNIST, the GDSR, BC14, and ImageNet. And we conducted experiments over 10 different models with different architecture and philosophy. And for all of these experiments, we have reached 100% of the attack success rate for both white box and gray box scenarios. And we have no influence on the clean model accuracy, which means that our attack will not affect the main test. And also mentioning that for the last 2 lines, they are vision transformers, and our attack is first effective backdoor against the vision transformers. And for the trigger generation, they are very efficient. Actually, we can find over 1,000 watermarks within just 2 seconds. And the collision is extremely rare. So This is already verified by the previous result that we have no influence on the main attack performance. But here we show that as we increase the length of the predefined pattern, we can instead decrease exponentially of the collisions to zero. And also for the statistical truth, our trigger string passes all the least randomness test, which means that the late call patterns in the pixel domain makes it difficult to identify our triggers. And also, we evaluate our attacks against all kinds of defenses and robustness in the state of art. And we selected three different groups, which is the input analysis, which examines the polluted images, and explanation-based analysis, which inspects the neural network's behaviors, and runtime detection, which detects the models of samples based on activation states. And actually, our text covers all of them. So for the conclusion, we propose a novel code architecture including attacks against the machine learning models. So we designed an attack with many basic properties we have as our goals, as I mentioned. And we validate the effectiveness of our attacks through both theoretical and the experimental validations. And we demonstrate that LoneNeuron can escape all of the defenses. And we demonstrate the feasibility and effectivity of the traditional powerful attacks by compromising a single link on the machine learning model supply chain. And I will call for further attention to the security of the machine learning source code, which deserve the same level of protection as the software. Thank you so much.
Question for Leon? At the beginning, you mentioned that you are collecting observability from images. How do you use those parts?
Actually, there are a lot of participants, but finally we collected 400 feedbacks from them. Just many of them just don't respond to our.
And what was the subject of the survey? It was just like where they get their software from?
Actually, we asked them a series of questions. So, have you used the downloaded the models from the internet before? And what measures will you take to mitigate the risk it might contain inside the model you downloaded? For example, the fine-tuning, pruning, and so on. So for each question, we let them select.